we're looking at trig from, well, we have looked at trig from the circle perspective, the graphing perspective. Now we're going to look at it from the algebraic perspective or equation perspective. These are trig identities. So we're going to start off with the basic identity. So we have our reciprocal identities. Okay, these are our reciprocal trig ratios. Okay, they're defined in this way. So, and when we call them identities, they are equivalent. So what we're going to do with these identities is we can replace any expression of cosecant with 1 over sine and vice versa. Okay, same thing here. We can replace a 1 over tan expression with cotan. Okay, and we can do that anytime we want because these are what we consider identities or equivalents, algebraic equivalents. Same here. Tan theta is equal to sine over cos. It doesn't matter what the angle is. For every angle, these are the same. So if I were to graph the equation sine over cos, I will get the same graph as tan. They just graph right on top of each other. These are quotient identities because these are formed with using a quotient of sine and cos. So algebraic identities are algebraic equivalents, and you can use these identities to replace equivalent expressions. So an example here, we know that tan theta and sine theta over cos theta are the same. It doesn't matter what the theta is, at 45 degrees or 30 degrees, doesn't matter. These expressions are equivalent. So anytime I see a tan expression, okay, like for example here, I can replace that tan expression with an equivalent sine over cos expression. Okay, so these two expressions are exactly the same, okay, because I've just replaced like with like. And this is one of the things that we can do with identities, since these identities are always true, meaning that this tan theta is always equal to sine over cos no matter what the angle is. And we can test it with numbers, doesn't matter. We can graph it. If I were to graph sine over cos, it's going to graph exactly right on top of the tan theta for all values of theta. For our identities, we want to look at also odd and even identities. Okay, and these are physical properties of graphs. So algebraically, and we've seen odd and even identities before. Okay, we talked about them. We haven't identified them as odd and even yet, but we're going to now formally talk about these identities as odd and even. So odd is defined as this. We have, if we take the negative x value of f of x, it equals the same as the f of the original x, but a vertical flip. So what it's essentially saying is a horizontal flip is equivalent to a vertical flip. We've seen this before with sine. Okay, so anything that has this type of symmetry, so this here's our odd symmetry. Okay, if I vertically flip this, okay, if I take this sine function, okay, I'm going to do a vertical flip of this, it's going to be equivalent to a horizontal flip of this graph. Okay, so and vice versa. So I'm going to do, I say vertical flip. Okay, so that vertical flip is the same as if I took that black graph and did a horizontal flip. And this is the property of an odd function. Okay, and even functions have a type of symmetry which is a folding symmetry. So this is what we call rotational symmetry. So if I spin it, this one has folding symmetry because if I fold it across that line, the left side matches the right side. Algebraically shows up like this. If I go in the negative x direction, if I go like this, the y values match if I go into the positive x direction. So if I take this positive x, I'm going to get the exact same y coordinates for negative x as I do for positive x. Okay, and this is a property of even functions. They have this folding symmetry. Now they're given the names odd and even because odd polynomials actually have this function. If you think of odd polynomials like a cubic function, they have this rotational symmetry. Okay, so if I take a look at x cubed, it looks like that. Okay, and I can spin that around. Even functions come from even, the name even function comes from even polynomials, like for example, x squared, a quadratic, that has folding symmetry. Okay, so this is where the odd and even names come from, but essentially, even identities are when we can fold across like this, and it looks like this. Negative f of negative x equals f of x. For odd, the rotational ones, we can say that the horizontal flip and the vertically flip are equivalent. So the identities that are odd and even for us, well, sine is an odd function, cos is even. Okay, if sine is odd, the reciprocal should also be odd. So cosecant is odd, and the same happens for secant. Secant, the reciprocal is still even. For tan, if we take a look at the tan graph, tan has this shape. Okay, so that is rotational symmetry, so falls under an odd function. And then the cotan must also fall under that identity. And if we take a look at from a circle's perspective, so again, we're kind of trying to match these three different perspectives. We have our graphing perspective, okay, or when we talk about the symmetry on the graphs, the algebraic symmetry looks like this. These are identities. We can also look at it from the circle perspective. If I take a look at sine, sine is the positive side and negative sine are just upside down versions of each other. This is odd. So if I go in this direction, positive sine gives me positive y, negative sine theta, sine of negative theta gives me negative y values. That is an odd symmetry. Okay? Even symmetry means that if I go in the positive direction, I get the same x coordinate as if I go in the negative direction. Okay? And that's going to give us this type of symmetry on a graph, and it looks like this. So odd is going to be folding across here. Okay, that's our sine functions. It has this odd symmetry across 90 degrees, whereas even functions like cos have this symmetry across that horizontal line. Okay, so we can match up all three types of symmetries from three different perspectives, or say the symmetry from three different perspectives: algebraic, graphical, or circle. So for most people, they seem to find that the graphical symmetries are much easier to kind of understand. But we're going to start using these algebraically.